All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is Colligative Properties Calculations Part 2. You're going to need a calculator and a periodic table for this one. And if you haven't done the first two questions on vapor pressure, then you really need to go back and take care of those first before you attempt these more challenging questions. And so here we go. Number 3 says the normal freezing point of benzene, that's C6H6, is 5.50 degrees Celsius. When 7.14 grams of naphthalene, that's C10H8, are dissolved in 45 grams of benzene, the solution freezes at negative 0.82 degrees Celsius. We're to calculate the molal freezing point constant for benzene from this data. So here we go. Remember that the normal freezing point without anything added to the solute, or solvent rather, is 5.50. Once you add the solute to the solvent, we have a new freezing point. It's negative 0.82 degrees Celsius. So we want to use that information to calculate the K sub F. We're looking for the molal freezing point constant for benzene. All right, so here we go. We're going to start with a basic formula of delta TF is equal to K sub F times molality. Right? That's how we calculate freezing point depression. K sub F times molality, the constant times the molal ratio. So let's do a little bit of rearranging. Now we've got K sub F is equal to delta T sub F divided by molality. So we're going to need to do some preliminary calculations before we can plug these in. So here we go. First of all, the change in temperature, freezing temperature. Well, we've been told that the original temperature was 5.50 degrees. So we're going to take the final minus initial. So negative 0.82 minus 5.50 degrees Celsius, and that's going to give us negative 6.3 degrees Celsius. So that is the change in temperature. It's dropped. It's a negative 6.3 degrees Celsius. So now let's calculate the moles of solute and the kilograms of solvent, right? The moles of naphthalene and the kilograms of benzene, so that we can calculate molality. So to do that, we're going to take what we've been given, 7.14 grams of C10H8 times 1 mole of C10H8. The naphthalene has a mass of 128.18 grams of C10H8. So when we do that calculation, we get 0.0557 moles of naphthalene. All right? Now let's calculate the number of kilograms of the benzene that it's dissolved in. So how do we do that? Well, here's what we do. What we're going to do is we're going to take the number of grams of benzene, we'll put that over 1 and divide by 1,000. That's it. That's going to give us the number of kilograms of benzene. We've got 0.0450 kilograms of benzene. So now it's time to start plugging in. Molality, remember, is moles of naphthalene divided by kilograms of benzene. And we get these numbers for those. We have 0.0557 moles divided by 0.450 kilograms. Moles of solute divided by kilograms of solvent. Moles of naphthalene divided by kilograms of benzene. And now what we're going to do is take those, and that, by the way, is equal to 1.24 molal. 1.24 molal. So now what we're going to do is we're going to plug into the KF equation. So we have K sub F is equal to the change in temperature, which we calculated to be negative 6.32, and we're going to divide that by 1.24, right? And that's going to give us this number, negative 5.10 degrees Celsius per molal, right? Per molal. And that is the unit, by the way, for K sub F, the molal freezing constant. That'll do it for number 3. Let's look at number 4. Number 4 says this. Number 4 says, what are the boiling and freezing temperatures of the solution in question number 1? It contains 7.50 grams of formic or HCONH2, that's formate, in 1.50 times 10 squared grams of water. For water, K sub F is equal to negative 1.86 degrees Celsius per molal, and KB is equal to 0.51 degrees Celsius per molal. Now, they've given me the K sub F and the K sub B, the freezing constant and the boiling constant. So I'm going to use those to help me analyze this problem. So let me start with my first two major equations, and they are as follows. By the way, HCONH2 is formamide. HCONH2 is formamide. So we're going to start with the number of grams of formamide. It's 7.50 grams of formamide divided by 1 just to hold the place, times 1 mole of formamide per 45.05 grams of formamide. You can use your periodic table to verify that, and that's equal to 0.166 moles of formamide. So now I've got the number of moles of solute. Let's go to kilograms of solvent. Just take the 1.50 times 10 squared grams of water over 1, divided by 1,000, and that's going to give us the number of kilograms of water, right? So now I've got enough information to get the molality. So molality then is equal to moles of formamide divided by kilograms of water. That's equal to, let's see, 0.166 moles of formamide divided by 0.150 kilograms of water. When I do that calculation, I get 1.11 molal. 1.11 molal. Now let's calculate the change in freezing temperature. The freezing temperature change was equal to negative 1.86. That was the K sub F. Negative 1.86 degrees Celsius per molal times, we've just calculated the number of moles of, or the molality to be 1.11 molal. That's equal to negative 2.06 degrees Celsius. Now let's calculate the change in boiling temperature. It's 1.51 degrees Celsius divided by molal times 1.11 molal is equal to positive 0.57 degrees Celsius. So we know the change in freezing temperature now and the change in boiling temperature. Let's calculate the actual freezing point and boiling point. Well, we know that water freezes at 0 degrees Celsius, so when we drop it by the 2.06 degrees Celsius, we get negative 2.06 degrees Celsius. The boiling point is going to be increased by 0.57 degrees Celsius, raised to 100.57 degrees Celsius, and that will do it for this problem. Let's move on to the next one. The next problem says this: what will be the freezing point of a solution made by dissolving 125 grams of calcium chloride, that's CaCl2, in 1 kilogram of water? For water, the freezing constant is negative 1.86 degrees Celsius per molal. So how would we do this? Well, let's start with our basic formula. The change in freezing temperature is equal to the molal constant, freezing constant, times molality. So what we're going to do now is we're going to determine the number of moles of CaCl2 we've got. So we're going to say 125 grams of CaCl2 divided by, check me on your periodic table and calculator with this one, 110.98 grams of CaCl2. When I divide those, I get 1.13 moles of calcium chloride. Now, here's what we're going to do. We're going to calculate the molality. That's moles of CaCl2 divided by kilograms of H2O. So molality is then 1.13 moles of CaCl2. That's what we've calculated for the number of moles of calcium chloride, divided by 1.0 kilograms of water. Now, here's what we've got to do, though. This is important. Folks, we're going to have to multiply this 1.13 molal that we got by 3. The reason is that colligative properties are dependent upon the number of particles. That's very important. Remember that when CaCl2 is dropped in the water, it's going to become this. When CaCl2 is dropped in the water, it's going to become Ca2 plus 2 Cl minus 1s. That's 3 different particles, 1 here and 2 here. So we're going to have to multiply that by 3 to get the molality of 3.39 molal, the final molality of 3.39 molal. Let's use that number then to determine the change in temperature, freezing temperature, and the change in, ultimately the freezing point. So here we go. The change in temperature then is equal to negative 1.86 degrees Celsius per molal times 3.39 molal. That's equal to negative 6.31 degrees Celsius. We're going to use that number to determine the freezing temperature of water, of this water. So originally the pure water had a freezing temperature of 0.00 degrees Celsius. We're going to drop that by the freezing temperature change of negative 6.31 degrees Celsius, and we get negative 6.31 degrees Celsius. That's the final temperature of the freezing temperature of the water. That'll do it for the last one. I'll see you in the next video. See you later. Bye-bye. Thanks.